Last week, Iran's bombing campaign sent shockwaves across the Gulf. Political shockwaves above ground. But weeks earlier, a different kind of shockwave moved silently beneath it. On the morning of February 1st, 2026, the floor of the Persian Gulf ruptured. A magnitude 5.2 earthquake struck just 10 kilometers below the seabed, shallow enough to drive seismic energy straight upward through the water and toward the coast of the United Arab Emirates. 361 kilometers away, residents in downtown Dubai felt their towers sway. At 828 meters tall, the Burj Khalifa absorbed the motion without visible damage. It held. After escalating military tensions and renewed regional instability, engineers are asking a harder question. Did those shockwaves quietly compromise the foundation of the world's tallest tower? Dubai is not built on bedrock. That single fact sits beneath everything else in this story. The city rises from a mixture of coastal sand, loose carbonate deposits, and weak sedimentary rock. In most parts of the city, solid bedrock lies more than 75 meters beneath the surface. Most of the world's super tall structures anchor directly into hard stone. The Burj Khalifa cannot. It rests instead on a deep engineered pile system, a manufactured foundation designed to compensate for ground that could not offer what the building needed. Every assumption of stability built into this tower was not discovered beneath the soil. It was calculated, constructed, and placed there by human hands. Since its opening on January 4th, 2010, 16 years and 60 days ago from today, the Burj Khalifa has been one of the most intensely monitored structures on Earth. A structural health monitoring program runs continuously, measuring foundation settlement, column strain, lateral displacement, and dynamic behavior in real time, 24 hours a day. The building was designed by Skidmore, Owings, and Merrill of Chicago. Geotechnical engineering was handled by Hyder Consulting. An independent peer review was conducted by Coffee Geosciences. The foundation design was tested against wind loads, seismic loads, and long-term settlement projections. The expectation was predictability. For most of the building's life, the data delivered exactly that. And that consistency became the foundation of a broader assumption that what it held would continue to hold. That was the comfort. That was also the risk. Here is the paradox at the center of this story. The Burj Khalifa was engineered to sink, not catastrophically, but measurably, predictably, within limits. Engineers placed 192 reinforced concrete piles beneath the tower, each 1.5 meters in diameter, each drilled 50 meters into the ground, anchored to a concrete raft 3.7 meters thick, weighing 500,000 tons. The foundation system did not reach bedrock. It could not. Instead, it relied on friction, the grip of surrounding soil against each pile shaft, transferring the building's immense load downward and outward. During construction, the raft settled approximately 75 millimeters, about 3 inches. That number was not a warning sign. It was the design performing exactly as intended. Engineers had modeled it. They had planned for it. They had accepted it. What they could not fully model was what would happen to that soil over the following 16 years, under repeated seismic loading, rising urban density, and falling groundwater. The February 1st event was not exceptional by global standards. A magnitude 5.2 earthquake is a moderate quake, but context matters. The Persian Gulf is not a geologically quiet body of water. The Zagros fault system in Iran, directly across the Gulf from the United Arab Emirates, is one of the most active tectonic convergence zones on the planet. In the past 10 years alone, 515 earthquakes of magnitude 4 or higher have occurred within 300 kilometers of the United Arab Emirates. That averages to one seismic event every 7 days. The February 1st quake struck at a depth of only 10 kilometers. Shallow earthquakes transmit energy more efficiently upward than deep ones. At that depth, the ground beneath Dubai did not merely tremble. It received a direct mechanical pulse, the kind that engineers call a shockwave input event. The kind that, over time, changes what sits beneath a foundation. The Burj Khalifa was designed to handle seismic stress through structural stiffness. Cross-bracing beams, braced panels, and a hexagonal reinforced concrete core work in combination to resist lateral forces. The building is rated to withstand earthquakes up to magnitude 7. That is a significant engineering margin. But the concern in this story is not a single catastrophic event. It is cumulative effect. Each seismic pulse, even a moderate one, introduces lateral stress into the interface between pile shaft and the surrounding soil. The foundation rests in calcareous rock, a carbonate-based material that is softer and more granular than granite or basalt. Repeated shockwaves alter the friction coefficient at that interface over time. When friction changes, load distribution changes. And when load distribution across 192 piles shifts unevenly, the process that engineers call differential settlement becomes a possibility rather than a past event. Add to that a second, parallel process: groundwater depletion. Dubai's groundwater usage significantly exceeds natural recharge rates. When water is removed from underground layers, the pressure supporting overlying soil decreases, and that soil compacts. When surrounding soil compacts at uneven rates, the piles no longer sit in the same material they were tested against. The system changes, quietly, continuously. The structural concern does not travel alone. The Burj Khalifa sits at the geographic center of one of the most intense urban construction programs in recorded history. Since the building opened in 2010, dozens of super tall towers have been added to downtown Dubai and its surrounding districts. Each new structure loads the ground, and each new foundation system alters the underground stress field. In geotechnical engineering, adjacent foundations are never truly independent. They interact through shared soil. A pile loaded by one building changes how the soil behaves around its neighbors. The cumulative ground loading of central Dubai today is fundamentally different from the conditions modeled during the Burj Khalifa's original design. The soil beneath the tower has been subjected to 16 years of seismic cycling, groundwater withdrawal, and adjacent structural loading, none of which was fully anticipated in the original settlement analysis. The engineering response to these known risks has been real and substantial. Dubai classifies all buildings to a seismic zone 2A standard, significantly more conservative than the city's natural seismic classification would require. Settlement monitoring at the Burj Khalifa has been continuous. Pile load testing during construction reached 64 meganewtons, among the highest loads ever applied in a civilian foundation program. These are not small margins. They represent serious, deliberate engineering. But here is the boundary of what engineering can do. Margins are not permanent. They are calculated against conditions that exist at a point in time, the soil conditions of 2004, when ground investigations began. 22 years later, those conditions have evolved. The monitoring continues. But what the sensors measure today is the response of a system that has aged, loaded, and vibrated in ways the original models approximated, but could not exactly predict. the Burj Khalifa is not in imminent danger. That statement is supported by the documented evidence and by the continuous monitoring data that has been collected since construction. What the February 1st earthquake, 31 days ago, actually revealed is something more important than a structural threat. It revealed that the ground beneath this building is not static. It never was. Stability. For a structure of this scale, built on this geology, in this seismic neighborhood, is not a condition that was established at construction and then held permanently. It is an ongoing negotiation between engineered systems and a changing Earth. The tower stands. The sensors transmit. The soil beneath it compacts, shifts, and absorbs shockwaves at rates that no original model fully captured. That is not a failure of the engineers who built it. It is the honest boundary of what engineering, at any moment in history, can know about the future.